The notion of a linear combination is usually discussed in the context of vector spaces. But you can have linear combination of other objects as well. For example, if x, y, and z are variables, then something that looks like this, where a, b, c are numbers, is a linear combination of their variables x, y, z. But for our purpose here, we'll stick with vector spaces. So let V be a vector space, and the scalars are from a field F, and suppose that V1 up to Vk are vectors in V, then lambda 1 V1 plus all the way to lambda k Vk, where lambda 1 up to lambda k are scalars, then this is called a linear combination of V1 up to Vk. Now, one interesting fact is, if you add two linear combinations of V1 up to Vk, you also get back a linear combination of V1 up to Vk. For example, say my two linear combinations are lambda 1 V1 plus all the way to lambda k Vk, and my second linear combination is alpha 1 V1 plus all the way to alpha k Vk. And using the properties of scalar multiplication and vector addition, I can rewrite this as lambda 1 plus alpha 1 V1 plus all the way to lambda k plus alpha k Vk, which of course is a linear combination of V1 up to Vk. Now let's take a look at some examples. Suppose I have two vectors in R2, then something like this is a linear combination of the two vectors. And let's take two vectors in the vector space of 2 by 2 matrices with real entries. Then something like this is a linear combination of the two matrices. And for the vector space of quadratics in X, everything is in this form, so we can say that this is a linear combination of x squared, x, and 1. Now, given a set of vectors v1 up to vk in some vector space V, the span of the set v1 up to vk is defined to be the set of all linear combinations of v1 up to vk. And it is denoted by span, open bracket, the set of vectors, then close bracket. So for example, if S is a set of these two vectors from R2, then the span of S is precisely R2, because every vector in R2 is given by AB for some real numbers AB, but this can be written as A times 1, 0 plus B times 0, 1, so as a linear combination of these two vectors in S. Incidentally, if you look at the set T consisting of these two vectors, 1, 1 and 1 minus 1, the span of T is also R2. And the way to see it is as follows. So I want to express AB, a generic element in R2, as a linear combination of these two vectors. And what you can do is simply take this linear combination. So this is a linear combination of the vectors in T. And you see that we can get all possible vectors in R2 by taking a linear combination of them. So it's quite possible for many different sets to have span equal to the same set. And finally, we're going to look at the following result. Let V be a vector space, and V1 up to Vk be vectors in V. Then V contains the span of the set V1 up to Vk. We'll now prove this for the case when k is equal to 2. And the general case can be proved by using induction. So let's take a couple of scalars, alpha and beta. By closure of scalar multiplication, we know that alpha times v1 and beta times v2 are in the vector space V. And now because both alpha v1 and beta v2 are in V, by closure of addition, their sum must also be in V. And that completes the proof. Now there's one more fact. If you take the span of a set of vectors, it also gives you a vector space under the same vector addition and scalar multiplication as the vector space that you take the vectors from. And this is a very useful fact because it allows us to ask the question, when is the span of the set of vectors equal to V? And in the case when we can write the vector space as a span of a set of vectors, that means we have a succinct description of all the vectors in the vector space. Every one of them is just going to be a linear combination of the vectors in that set of vectors.